All right, welcome to part two of my Monte Carlo simulation in Excel without macros. And I'm going to do this in one take. I'm going to do it live. And hopefully I'm going to go pretty fast and keep this relatively short without a lot of the math and statistics that goes into it. And I may say a few things that my econometrics professor would just cringe at, but I'm going to keep it simple. It's been 25 odd years, probably more, now that I think about it, since I took statistics or econometrics. So some of these concepts are a little bit fuzzy for me, but I get the basics of it. So, anyways, Monte Carlo simulation is just a way to run many different iterations or runs of a scenario so that you can get a relatively decent picture of what the expectations should be rather than, say, linearly modeling something. So, in my example, when we're doing retirement balance forecasts, you could do a flat, 8% rate of return over a period of time, 8 years, 10 years, 20 years, doesn't really matter. But that's a constant linear rate of return. That's not realistic and not really representative in real life. You can do that and it will give you a reasonable, expectation. But if you want to see kind of all the randomness of what real life could possibly do, a Monte Carlo simulation can help with that. There are different issues with Monte Carlo simulations. I'm not going to go into it, but it's a reasonable model to forecast something. The one requirement with doing what I'm going to do right now is that the data or the samples that you're using to help you forecast the model should be normally distributed. And all that means is that when you look at all of the possible results in your population or sample set and plot them out, you're going to get a bell curve, which kind of looks like this, okay? And I verify that the S&P 500 annual returns are in fact normally distributed. When you get to like daily returns for the S&P 500, it may not be, but on an annual basis, it is. So when you look at this type of distribution, what you tend to see is that there's a peak, and that's what would be called the mean or the average of the population or the sample. And then how spread out the shape is described by what's called the standard deviation. And I've calculated both here for the S&P 500. So here's the mean and here's the standard deviation. Okay, and you can see that in fact the mean is about 12% if I was to draw this straight up. And then, like I said, standard deviation is how spread out the results are. The larger the standard deviation, the lower this peak will be, but the curve will be spread out more and it will be a little bit flattened. If that standard deviation was lower, the peak will be higher and everything will get kind of squished in. So standard deviation describes how spread out the data is. So when you have low standard deviation, it just means that your result cluster more strongly around that mean. Okay, that's the only requirement to make this modeling work. There are different distributions that the data can follow, and you would use different models to represent that. But for our case, as long as data is normally distributed, the method I'm going to show you is going to work. So some examples of other types of data that could be normally distributed would be things like, the heights of males in the human population, the weight of females, between ages 20 and 25 in a particular country. Things like that tend to be normally distributed. Something else that may be normally distributed would be, say, cost for construction, right? You may look at a particular material, say tile or carpet or whatever, and you would expect, an average cost of whatever per square feet. But then there are variances, in terms of supplier, the quality, whatever, that will make it more expensive or less expensive. But those things tend to be normally distributed as well. So if you're a quantity surveyor and you want to forecast the project cost, you can use this as well. All right, so now that we know what normal distribution is and know that S&P 500 annual returns are normally distributed, we can go ahead and build our model. So what I'm going to do is I'm going to just create a new sheet, and I'm going to set up a couple of things. Year, starting balance. And like I said, I'm going to do this live. Contribution, gains, and ending balance. And then the first thing I'm going to do is I'm going to set my sheet to calculate manually. That just means that it's not going to do the math live until I recalculate the sheet. Okay, that just allows me to go a little bit faster. And in fact, you know what I'm going to do is I'm going to insert a couple of rows here. Insert, so that I can do a couple of things. Starting balance, and the reason I do this is so that we have one place where we're changing, some kind of input, and then the model will just readjust. So contribution, I'll do the same. All right. So for this particular example, I'm going to do kind of a 10-year model. You can, of course, take it out to 15, 20, 30 years, whatever you like. You can add more factors to the model. So I'm just doing very basic. It's starting balance, contribution, your gains, ending balance. Nothing about withdrawals or anything like that. No taxes, none of that. But once you understand the method, you can expand it and it would make sense. So the other thing I'm going to need is I'm going to insert a column, and I'm going to say rate of return. I'm just going to call it return percent. Okay. So the way gains would work is that it would be your starting balance. We're going to keep this simple, plus your contribution times your rate of return. And then your ending balance is just those three components. So starting balance, contribution, and gains. So we're assuming here that you're making all of your contribution at once at the beginning of the year, and that's why the gains is doing it all together. Okay, you can make it more complicated and monthly and all that jazz, but for this model, I'm going to keep it simple just so you can see the technique, and then you can expand it as you see fit. Okay. I'm making some of these columns bigger so that the numbers will make sense. And then the other thing I'm going to do is I'm going to turn this into dollars. And I'm going to turn my returns column into percent and 2 decimals. Make these dollars as well. And maybe we'll highlight this in blue just so we can see what's going on. The other thing I'm going to add here is S&P 500 mean and S&P 500 standard deviation. Okay, and we can actually calculate that. The mean is just average, and we'll use the entire return set here from 1926 through 2019, and I'm going to fix this range. I could have named it too, but I'm lazy. I'm going to fix this because I'm just going to copy this formula down for standard deviation, and instead of average, we're going to use stddev, and we'll use stddev s for sample. It's close enough. All right, so this is how it's going to work. We're going to copy this formula down to the rest of the cells, and we're going to recalculate. So starting in year 2, your starting balance will actually be your ending balance from the year before. But then everything else is the same, so I got to make sure that I fix this contribution. Okay, then I can copy this down, and I can copy these down. Once I have this, drag these formulas all the way down, and let's go ahead and recalculate the sheet. Okay, still 0, so let's put in a starting balance. So let's say that this person is 55, and we're doing a 10-year model because we want to see what happens when they get to 65. And I see that I need to copy down 2 more rows here to make it 10. So let's say that they're 55 and they have $500,000 saved up so far. Okay, and they're going to continue to contribute, but maybe they'll do $12,000 a year. So $1,000 a month. They're not maxing out, but that's okay, of their 401k. So when I do this, you can see that the ending balance is in fact growing, even though the rate of return is 0. And the reason for that is it's coming from contribution. Now, if I were to do a flat rate of return, like, say 10% or 8% or whatever, and copy this all the way down and recalculate, you'll see that the gains are now not 0 anymore, and the balance is growing. Okay, so that's basically how we're going to set this up. Now, to do our runs, and I'm going to do, like, I don't know, call it 50 runs, okay, or iterations. And this will be 1. This is going to be the next one, and we'll copy this. What are we, 41? So we'll go to like 91. Calculate the sheet just to make sure. Okay, I got 1 extra. And then on top, I'm going to put my year. And I'm going to do a paste special and transpose and keep the values only. Okay, so this is just getting 2020 through 2030. And, I can make this bold and make it blue so that I know it's kind of like the years. Right? And then on this row here next to iteration, I'm going to set this equal to the ending balance of each year. So 2020, 21, whatever, right? And to do that fast, I'm just going to kind of cheat. So I'm going to say F41. And I know that I have 10 of these, so I'm going to copy this down. Okay, and do I have 10? I have 17. So let's see where my 10 is. There we go, to 10. So delete this. Rather than typing, I'm going to copy this and paste special again. And we'll do formulas this time, transpose. And I'm missing 1, so it's actually 11 count, but that's okay. We can copy this over and make sure that this is 51. Okay, and if we were to recalculate the sheet, the values is going to be the same. And I'm going to make these dollars as well. All right. So now we kind of have our sheet set up, and we can go ahead and run our simulation. So what we need to do is to get Excel to fill in each of these cells in the table here to represent one run over the 10-11 year period from our base model here that's over here. Okay, and the way that we do that is the first thing we're going to do is we're going to randomize this rate of return, because right now we have a flat rate of return. And in fact, you know what I'm going to do is I am going to go graph this so we can kind of see it. We'll do like an area chart and just move it over here. At this point, I kind of like to call it ending balance or something like that, ending balance. And I like to turn off my grid lines just to make it cleaner. Maybe make this gray. So we'll go ahead and format chart area, give it a background, and we'll say solid, and then we'll pick like a light gray, something like this. Maybe even lighter. Okay, just to make it look nice. That's all it's doing. All right, so right now we're graphing the ending balance, but you can see that it's kind of just relatively straight line. Okay. And then the other thing I'm going to do, you know what, I won't do that now. Now we're going to randomize this return, because this is the whole point of the Monte Carlo simulation. So far in this model, we have done a flat rate of growth that we assume is 10%. That's probably high. You probably want to use something like an 8% if you're going to use a flat rate, but you know, whatever, it's fine. But in order to do a Monte Carlo simulation, we want to randomize this rate of return using characteristics of the actual S&P 500 annual returns from 1926 to 2019. And since we know that it is normally distributed, those annual returns, we can use a normal distribution function in Excel to give us that return. And the way you do that is you use what's called the norm inverse function. I'm not going to go into why, but you can see that it takes three items to make it work. Okay, so the first parameter for this formula is probability, the second one is mean, and the third one is standard deviation. For probability, this is where we're going to randomize the rate, and we're going to use the built-in Excel function called rand, which gives us a number between 0 and 1. If you take that to percent, it's 0 and 100%. The mean, we're going to use the S&P 500 mean. And I'm going to go ahead and fix that because I'm going to copy this down. And then the same for the standard deviation. So basically all this is doing is giving you a result that's based on a probability, which we're randomizing, and the characteristics of our population, which is the mean and the standard deviation of it. So given these two factors and a probability, this norm inverse function will give us a normal distribution result based on those factors. Okay, I'm going to go ahead and just copy this down. So when you go to formulas and recalculate the sheet, what you're going to see is that it's going to update these returns, but instead of being that flat 10% that we had modeled, it's now going to be randomized. But it's going to be randomized within the parameters of our population. And you can see that, you know, some years are negative, some are positive, some are larger than others. But overall, it's going to kind of match this parameter that we set. And you can see the graph changing as I do this. Okay, so every time I recalculate the sheet, you get a slightly different result. So here we can see this, the ending balance at 961 is probably the lowest we've seen, right? But if you keep doing this, this one's quite high, it's 4 million. If you keep doing this, you get a just random result that is following the market, you know, characteristics for the last whatever, 85, 95 years, something like that. Okay, so this is a little bit more representative of what you can expect than just a straight line return, because it really is random, right? You don't know what's going on. Now, I said before that there are some issues with Monte Carlo simulation, but for our purpose, it's better than using a flat assumption. Okay, so I'm not going to get into the issues. All right, so now the next question is, now that we've set this thing up, how do we go ahead and get 50 runs of this? Okay, you can do 100 runs if you want. And you know what? I'm actually going to just copy this down to 100 and whatever. I'm going to go ahead and do 100 runs just for the hell of it. Okay. One more. This is where things get interesting with Excel, and it's a nifty trick. So you can trick Excel into running 100 of these for you automatically. And the way that you do this is you use a data table. So we're going to highlight this entire range. Actually, you don't need to highlight the iterations. You can just do this. And I'm on a Mac. And on a Mac, you can go to the menu bar and select data and then table. And you're going to get the same thing that I'm going to show you. But if you're on a PC, it's located in a different place. So I'm going to show you where you get to that on the ribbon. So what you do is you go to the ribbon, you go to data, and then you go to what if analysis, and then you click on data table. So this method should work for both Mac and PC. But when you do this, you get this little pop-up that basically says, how do you want to set up your data table? And you'll notice that what we did here in the header of each column is to set it to the ending balance of each of these respective years that's coming from this other table over here, right? So what Excel is going to try to do is it's going to take these headers and kind of autofill the rest of the data table following this pattern. This is where the magic is. So in order to make this happen, we're going to kind of trick Excel by pointing to a blank cell for it to fill the rest of the data table. And then we're going to click OK. And until we actually click Calculate Sheet, it's just replicating. Oh, you know what? I needed to do iterations because it's skipping the first column. So let me do this again. Highlight the entire range, including my iteration column, data, what if, data table. In the column, we're going to pick a blank cell, hit enter, click OK, and there we go. That looks way better. So all the columns are properly filled out. And now when I click Calculate Sheet, it takes a couple of seconds, but you can see that all of these are random, right? It'll update and it'll be randomized. So I don't know if you're seeing that on the video. And we need to make these dollars as well, because right now they're not. All right. And then in fact, we can go ahead and grab this entire set and graph it, just so we can see the distribution of this simulation. So I'm going to go to Insert, Chart, and I'm going to do a line chart. And I'm going to move it up here, spread it out. Right now it looks kind of weird because what it's doing, and I'm actually going to make this a little smaller because I need some space over here. What it's actually doing is it's treating my data as columns. That's why you see 11 series representing the 11 years. And that's actually not how we want to graph it. So I'm going to right click on one of the lines, go to Select Data. And what I'm going to do is I'm going to switch my data between rows and columns. Okay, so I'm going to do that. And then go back up to the chart. So now my series is changed to 100 series, which is the number of runs I have. But I don't really care about that. It's just taking up space. I'm going to delete this legend just so I can see the chart better. And you know, like before, you can format this and you know, make the background gray to make it look nice. Whatever you want to do here. Okay. But the key here is that in this 100 runs, you see that there's a couple of outliers that's really high, but then there's a set of results that are like all clustered together somewhere in here. Okay, and that's what we're interested in. So what I'm going to do now is just do some calculations of the information here so that it makes more sense. Okay, so let's go ahead and get the average and the median of our runs, and then we're going to get some percentiles. So let's do 5 percentile, 10 percentile, and 25 percentile. And I'll explain what this all means, but for now, just follow along and see if you kind of get it. So average is just an average, and we're just going to use the average formula for that. And we're going to average it over the 100 runs. And again, we're going to fix this. So what I'm actually going to fix is the rows, but I'm going to let the columns change. Okay. And I'm going to do median as well. When your result is not that far out, so say you're going a year or two, the median and the average are going to be relatively close. You can see that here, 569 versus 565. I'm not going to go into what a median and an average is. That's the statistics. But normally I would use the median because it's more representative. The average tends to be affected by outliers a lot more. So if I recalculate sheet, you're going to see that when you're closer to the beginning, the two values are really close together. But as you move to later years, you can see that it's much more spread out. And in fact, the median is much lower than the average. And like I said, the average gets affected by the outliers. So it's better to use median. Okay. And the other thing we can do is we can just change this graph to, instead of plotting the ending balance here for one run, we're going to have it plot the median instead, okay, because that's more representative. We can also tell it to put the years on the x-axis. So that's more representative right there. Okay, so every time I do this now, you're seeing that this median ending balance, and in fact we can change that title, gets adjusted ever so slightly. So these are Monte Carlo distribution. We'll call it run or iteration distribution, just to be clear. Okay. But every time you do this, this gets updated. And the more time you do it, the more you're going to see that it's tending to follow a pattern. So I had seen a low value of 1.4 million in that cell and as high as 2 million. And if I keep going, I'm seeing that it tends to go between 1.4 something to about 2 million. So if I wanted to say, well, what could I reasonably expect having seen these result sets, you know, over 100 runs, and I keep clicking. So as I keep clicking, you know, I'm doing 100 runs, 100 runs. So far I'm probably doing, you know, over 1,500 runs because I've at least clicked 15 times, okay? But it's giving me an idea and a picture of what to expect. And like I said, what I'm seeing is that anywhere between 1.4 something million to 2 million. So let's call it 1.5 to 2 million. So an expectation would be somewhere between those two values, like say 1.75 million. And I would say that that's probably a reasonable expectation over many, many different runs, because that's what I'm seeing as a characteristic return here, right? The other thing that you may want to do is to show the percentiles of the results. So we're going to do that now. We're going to use this formula as a start. But what we're going to do is we're going to use the percentile, and we're going to use percentile inclusive. And that just means that it's going to include the two end values, the two boundary values, okay? And this formula takes two parameters. The first is your array or your set of result. And then the second parameter, the k, is what percentile you want it to calculate on. So we're going to fix this to column J. And then we're going to copy this down so that it's referencing the right percentile. And then we're going to copy this across. And I'll explain briefly what percentile means so you can understand it. And again, we're going to calculate sheet, let this update. Okay. And you can do this as many times as you want. Okay. So let me go ahead and explain this percentile. So the 5 percentile means that this result here is better than 5% of the lowest result in the 100 runs for each of these ending years, 2020, 2025, 2030. Okay. The 10 percentile means that you are going to be more than 10% of the lowest result in each of these years. And the 25 percentile means you're going to be 25% more than the lowest results in each of these runs. That's all it means. Okay, so 5, 10, and 25 percentile. The inverse way of looking at it is that if you're looking at the result from the 5 percentile, you're going to be higher than 5% of the lowest results. But the inverse of that is that 95% of the time you can expect to be higher than this amount in your return. And the same thing with the 10 percentile. It basically means that there's a 90% chance that you're going to end up higher than this value when you run this many runs. And of course, 25 percentile means that there's a 75% chance that you're going to be higher than this value. So when you combine it with the median, it kind of gives you a reasonable window of expectation, right? So we're saying that for these parameters, we're expecting roughly an average of about 1.75 million. But that's 75% of the time, we're going to be higher than about 1.25 million, okay? And then the 5 and 10 percentiles just represents our worst case. If you wanted to, you can represent and graph these percentiles as lines on this chart on the left here, just so you can see what it looks like. So if I were to do that, I can go ahead and add some series. And let me go ahead and just add these. And it should create, okay, it wanted me to do it individually. All right, that's fine. So we'll do 5%. We'll do 10 percentile. So this is going to look like my model that I did. Yeah. I don't know why it's leaving this in here. That's annoying. Okay. Oh, come on. Let me check my data range again, because these series, that looks right. That looks right. And that's just not right. All right. Okay. So now we've added these series, and by default they're graphing as area charts, but we can just change the charts to lines for that particular series. And we'll do it for this one as well. And of course you can give them different colors. Okay. So basically the blue area is your median, because we're graphing this row. And then the 3 lines here represents the 25th percentile, the 10th percentile, and the 5 percentile. Okay, so this is giving you your 2 worst case, the case where 75% of the time you're going to be higher, and this is kind of the median expected case, right? And then you can just calculate sheets as many times as you would like in order to see how it shakes out over many different runs. But once you have this, you can modify it to make it more complicated, to cover different scenarios that you wanted to. You can, of course, change your starting balance. So if we say we didn't have $500,000 saved up, but only 250,000, what would that do? Calculate sheet. So that drops our ending balance to about $1 million, just above $1 million, right? Just off the bat. And you can keep running it to see, you know, what that result looks like. And you can just play around with it. But hopefully this technique is useful to you. Certainly you don't have to use it just for this application. You may have other scenarios where a Monte Carlo simulation would be helpful. And this is a way to do it in Excel without programming or writing macros or whatever. So in any case, I hope that you found this useful and enjoy. Thanks for watching.